Okay, so today we're going to talk about section 6 in chapter 3, and this is referring to related rates. So we've kind of talked about the derivative, of course, and then we've went through dealing with the derivative with respect to different letters. So if you remember the last section that we just finished with the implicit differentiation, and remember the rule was if you're taking a derivative with respect to x, basically, if you're taking a derivative of a y, another letter, you had to put that y prime there. Or you might see a dy dx, something like that. That was the chain rule. That was the implicit differentiation that we had to solve for. So we're going to take that to the next level here. In this case, we're going to talk with taking the derivative with respect to time. That's what we're dealing with when we deal with the rates, is anything that's changing versus time, like a speed of a car, like a production of something. It has to always do with how fast it's going. So show you we're not going to have a lot of homework. That's the good news. The bad news is it does take a little bit longer on some of these to set up. So I want to make sure you're all seeing and understanding this concept here. So starting off here, they're going to jump right into an example. Now, as we do this, I'm going to pause it, maybe take the slide off the screen and show you what I mean here. In fact, before we actually get to this problem, show you what I want to do here. Okay, so we'll get to your homework in a bit. Just remember, so if you had this equation like this, and I asked you to take the derivative with respect to x. So remember how that works, right? So if we're taking this derivative, the derivative of this is going to be a 2x, the next one's going to be a 3, and the last one's going to be a 0. But of course, what we learned from implicit differentiation was that because we're taking a letter here, because this is not an x, the letter that we're taking the derivative with respect to, we had to put that little extra chain rule, which is that y prime. Okay, that was the implicit differentiation that we used last time. So it isn't going to be any different coming up if I give you the same problem. Show you something else we're going to do. Okay, same thing. We take the derivative of the first piece, which is the 2x. We take the derivative of the second piece, which is the 3. And instead of a y prime, notice it's exactly the same as if I said a dy dx. That was one of our first things we learned. That's the same as y prime, is a dy dx. Now, the reason I'm using this is it's going to matter for what we're doing today. This, excuse me, and this, same thing. Okay, same exact answer, same problem. Okay, but why I'm talking about that is, now let's say we have the same problem, but this time we're going to take the derivative with respect to t. Now the good news is not much changes. We still get a 2x here, we still get a 3, we still get a nothing over here. But remember what I talked about earlier here in this orange. We're taking the derivative with respect to t. So any letter that you take a derivative of that's not a t, you have to do that same chain rule. So let's not do it in orange, but this y right here, just like over here, this is going to be a dy dt. The letter that we're taking the derivative with respect to, that dt, that's on the bottom. And of course, because that was a y, that's a dy on top. And also, over here, we have the same problem. We took the derivative of an x. Because that's not a t, we have to find dx dt. It goes right next to it. So you may have a number of these, and you'll see how these work. But that's the key. Any letter that's not t right there, you have to do the chain rule, the implicit differentiation that we used last time, where it's d of whatever that letter is over dt. Okay, so what that is that's going to talk about the change of x with respect to time, the change of y with respect to time. And this is going to go the same for any problem. If I have an area equals pi r squared, and I tell you to take the derivative of that with respect to t, well, the derivative of a is just 1, but because it's not a t, I have a dA dt. In this case, excuse me, we We use the good old rule, bring the power up front. We have a 2 pi r, and again, because that's not a t, we tack on a dr dt right to the end of it. So that's your derivative of that formula with respect to t. And as we talk about what all this stuff means, remember, that means the change of a over the change of time. This means the change of the r over time. This is just the plain r. We're going to have letters, different pieces all incorporated here. That's what's going on here when we do these derivatives with other letters with respect to t. So keep that in mind as we're doing this, as you're seeing these PowerPoint slides, how this is going to work. Okay, that's the new part from last section that we're going to apply today. So a student is concerned with that the rate of their increase in financial aid is lagging behind the increasing costs of tuition and fees. So what does that mean? Well, a renter is concerned that the rent is increasing faster than his take-home pay. And see what's happening in both these different examples is one thing is increasing and another thing is increasing, but is it increasing fast enough or too fast? And that's a case, as you've probably heard in the news lately. We have high inflation in our country. So inflation is going up at a certain rate. Well, people had pay increases at a certain rate, but which one was doing better? Which one was increasing faster? And that helps you project what's going to happen in the future. So again, expected increase in car loan interest rates and decrease rate of sales, union workers, all these examples here. Okay, and the key is all the quantities are changing with respect to time. So that's what we're going to figure out. Everything, how are things increasing, decreasing, and relating to time. Now, the first example is kind of a unique one. It works more for a physics type class, not so much in the business class, but see if you can follow along with what's going on here. You have a ladder that's leaning against a wall, and it's a good example in the fact that this is something that everyday people could deal with. Maybe you've dealt with this, where you have a ladder that's leaning against the wall. The ladder is 26 feet tall. And what happens is the ladder starts to slide from the top of the wall and starts to fall down. Okay, so if you kind of look at the picture right here, you see there's a little tiny green arrow right here. This ladder is falling down. So if I look at it this way, here's my ladder, my 26-foot tall ladder. Now, what's happening is the ladder is starting to fall to the point where it's almost hitting the ground, and then at one point it's a 26-foot ladder on the ground like that. So those are kind of my progression steps. And like I said, you may have dealt with this where something's starting to fall. Now the key here is that the one thing that's constant is the ladder is always 26 feet tall. But the distance right here, this y, look at the y value, notice it's getting smaller and smaller till ultimately my y is nothing. Then you get x right here. It's a little value. That's a distance from the ladder to the wall. And then as the ladder falls, notice how that x gets bigger and bigger. Then ultimately, right here, x is the length of the ladder is 26 feet. So x and y are changing, those lengths, those distances. Y is dropping, as in the distance is getting smaller, whereas x, the distance is getting bigger. And at different points, it's happening at different speeds. So when you look at this, and again, kind of think about it, if you ever drop something like a ladder, in the beginning, the ladder's slowly starting to fall. Then at the very end, it's like going out of control. It's going so fast that you can't do nothing about it. And that's the kind of thing we want to see is at any given snapshot in time, we want to pretend like we're taking a radar gun and saying, well, what's the speed of this y decreasing? What's the speed of this x increasing? That's what they mean when they say these related rates, when we're talking about changes of different letters over time. And it's not the same, like I said, as these different ladder steps are happening. Y is increasing really fast, decreasing really fast when the ladder is about to hit, whereas in the beginning, the y is not increasing so much. And that's the kind of thing that we want to talk about. That's the comparison that we're going to be making here when you look at all these problems. Okay, so how does the math work out here? How are we going to apply this? So we need an equation first. Okay, an equation that already talks about the connection between x and y. All right, so that's an easy equation if you look at it here. So the question they ask here, let me get to that. If the top of the ladder slides down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? Okay, so there's a couple different things that go on into play here. Sometimes it's falling at a steady speed, sometimes it's just falling really fast. In this case, what they're saying is the ladder is falling at 2 feet per second. So it's almost like pretend there's a rope right here and somebody's lowering it at 2 feet per second. And as that's happening, of course, the ladder's going further and further out until it hits the ground. They want to know what's the speed of x increasing. So the key here is you're going to get a lot of different variables. Okay, remember we have x and y, and when we do these derivatives with respect to time, you're going to see a dxy. You're going to see, a dxt and a dyt. Those are basically different letters. Those are the speeds, whereas x and y are the actual distances. So how we're going to do this? We have to create an equation. I'll give you the kind of a game plan. Every one of these, you need to make an equation that has all the letters in it, like x and y. Then you're going to have to take the derivative of those, and then you're going to have to remember the chain rule, and then you start plugging in numbers and see what you get. So what's the equation? Well, we have to remember this is assuming this is a perfect 90-degree wall, there is a, excuse me, kind of skip right here, there is a 90-degree, there's the Pythagorean theorem. You can make the x squared plus y squared equals 26 squared. Okay, now remember what's interesting about that is, remember all those different triangles, those different ladders I showed a minute ago, all of those hold the same equation. Whether the ladder is about to touch the ground, or the ladder is at a 45-degree angle, or it's right at the top, it's always true that x squared plus y squared equals 26 squared. So what we're going to do is we're going to take that equation, we're going to find the derivative because that's going to give us our changes. So we're going to take it with respect to t, as I showed you earlier when I took the slides off the screen. So go back. You see right here, that bottom equation, you take that derivative, that's a 2x. That's going to be a 2y, and of course, that's a 0. But because we're taking the derivative with respect to t, I have to do the chain rule. That's a dx dt when I take that derivative of x. And when I take a derivative of y, we get a dy dt. So this equation right here is your derivative, and that's going to tell you all the things that matter here on this equation. And you see that's the one that we have up here on the slide. Okay, 2x dx dt plus 2y dt, dy dt, sorry. And look at that equation on the top here. That is the derivative, and it contains 4 different variables. Okay, even though there's some shared letters, I just want you to see. X is a variable. Dx dt is a variable. Y is a variable. And dy dt is a variable. All 4 of these mean something different. Remember, this is the distance of the ladder, I'll say the base of the ladder, to the wall. Y is going to be the distance from the top of the ladder to the ground. Again, look at the picture. You can see what's y? It's the distance from the top of the ladder to the ground. Now dx dt, anytime you see a letter d, that letter over dt, excuse me, that is the rate of change. And in this case, it's the rate of change of x. How fast is x changing? How fast is the bottom of the ladder going away from the wall? That's dx dt. Dy dt is the rate of change of y. So when you hear dy dt, it's saying how fast is the top of the ladder falling down the wall? How fast is that distance y changing? That's what these 4 letters represent. And this is the most important part because you need to figure out where do you plug in, what plugs into what. So I'm going to go back to the problem a second. I know it's hard to read because I wrote over it here, but notice that the one information they gave us is, okay, the top of the ladder slides down the wall at 2 feet per second. Okay, so they didn't tell you the top of the ladder is 2 feet away from the ground. They're telling you the top of the ladder is going down at 2 feet per second. That tells you, out of these 4 variables, we're talking about that one right there. That's the dytt. How fast is that y changing? How fast is the top of the ladder going down? The other part they tell you is when the bottom of the ladder is 10 feet away. So what they're saying is bottom of the ladder is 10 feet away. That's this one right here. Notice it's not telling you the bottom of the ladder is changing at a rate of 10 feet per second. It's not a rate. They're straight up telling you the distance of the bottom of the ladder to the wall is exactly 10 at a certain point. So remember I showed you that ladder as it's falling and falling. It's like when the ladder is 10 feet away from the bottom of the wall, freeze. Take a picture right there, and that's the snapshot we're taking. That's when we're going to try to figure out all these different rates. Okay, so the question they're asking is, at what rate is the bottom of the ladder moving away from the wall? So they're wondering, what is this right here? What's dx dt? How fast is that going? So you have to always identify, what are all my variables? What are they giving us? And they don't just tell you what x is this, or dy dt is this. You have to understand what the meaning of those are. And from the word problem, you take that info and you plug it in. So we had the equation. We found our derivative. That right there. Now we have to figure out what everything is. So they tell you that dx dt and dy dt are related through this derivative result. And we knew it's a related rates problem. So now I'm going to erase everything. I'll rewrite anything I have to here. So dx dt is what we're trying to find. So this letter right here, this is the one that we're looking for. Okay, remember I said they asked us how fast is the bottom of the ladder moving away from the wall. They're asking you how fast is x changing. Okay, they tell you x is 10. So we're going to plug in a 10 right there. And then they tell you the top of the ladder is going down. Remember, it's dropping at 2 feet per second. And here's the important part. It's going to be a -2 right here because of the fact that it's a decreasing amount. Y is getting smaller and smaller, so my dy dt is going to be a negative number. Now remember, there's 4 variables here. They want us to find this one. In order to find that one, I have to know the other 3. Well, I know the x, I know the dy dt, but I don't know this y right here. Well, there is a way to find it. Okay, go to the next slide maybe. Okay, back to the fact that the ladder is always a perfect triangle. It's always going to be y squared plus x squared equals 26x squared. I don't want to know what y is. Well, they're saying when x is 10, I can plug that in for the x right here. And I can use this original equation to solve for y. We plug that in, we get, and that should be 26 squared, just so we're clear. But when you plug this in, and they didn't show the work for us here, but you get x squared plus y squared equals 26 squared. 10 squared plus y squared equals 576. And y squared is 476, and you get y equals a perfect 24. That's where they get this 24 from. So at the moment the ladder is 10 feet away, you have to know, because the ladder is always 26 feet long, that the distance down the wall has to be 24. So we have our last variable, that 24 right here, and now we go back and we could plug that into the equation. Okay, so back to our equation, right here at the very bottom left. Right here, we plug in all the pieces. So we plug in the 10 for x right here. We don't know dy dt, that's what dx dt, that's what we're looking for. We just found that 24 for y, and we were told that the dy dt is -2. Those are all my things that I'm going to plug into this equation. And you see what's left in that equation is go find dx dt, my only variable. So we just have to clean it up a little bit. So remember, this thing comes out to be all this on the right side. We move this over to this side over here. That's why it became a negative in front. And then we divide it by the 20. So they didn't show all the algebra, but that's what they did. They moved that over. They divided by the 20 out front. They got this, and it comes out to be 4.8 feet per second. So lastly, summarize what's going on here. This is dropping at 2 feet per second. And it's dropping constantly, but as it's going, this one is getting a different speed. So they're saying right when the ladder was 10 feet away, and they want to know how fast was it increasing. Well, it's increasing at a rate of 4.8 feet per second. So that's a first example of how we can use related rates to find anything here, anything that you need. The trick, like I said, is doing the derivative correctly, but really identifying what all those letters that you have mean. And you're going to get 4, 6, sometimes 8 different variables in a problem. You've got to know what each one of those things stands for, what they are. So this next slide sort of gives a little rundown of how to do it. I love doing a figure sketch if you can, just because it makes it easy to see and identify what you have. The big one that I mentioned, identify all the relevant variables. You're going to get all these d something dt, and you have to distinguish what's x, what's dx dt. They are going to be different things, so make sure those are clear when you're working on those. Then we have express all given rates, and rates to be found as derivatives, so that's where you're actually finding the derivative. And then get the equation, plug in that equation, or find the derivative of that equation. That's what we're doing here, and then you're going to plug in values and you're going to solve. So again, this is a good one to pause the video, screenshot it if you need to, or go download this PowerPoint just so you can kind of have this kind of next to you when you're doing these homework problems to help you out. Okay, jump to another example here. We have a westbound plane traveling at 120 knots, nautical miles, and it is 120 nautical miles from an airport. A northbound plane traveling at 160 knots passes directly over the airport. Okay? How fast is the distance between planes changing 1/2 hour later? Assume that the planes continue at the same speed and direction. Okay, so here's kind of what we have going on here. All right? So a westbound plane traveling at 120 knots is 120 nautical miles from the airport. Right? So this is how far they are. So let me kind of draw that. The picture is kind of different here, I'll tell you. This picture is showing their speeds, okay? But what's happening to start is you got a plane over here. This is plane number 1, which is 120 miles from the airport. And the example's kind of weak because it's got the same speed and distance, but this is how far it is, while there's another plane right above the airport. Okay, this is the initial spot of what's going on. Okay, this is the start. Now, what's happening is a few minutes later, again, pretend this is the airport still right here. If I can draw this, sorry, here's still the airport. Now, what's happened is this plane has gotten a little closer. And the plane that was overhead at the airport is now up here. So here's the airport, here's plane number 2, here's plane number 1. So it's moving in this direction, this one's moving in this direction. Okay? Then a few minutes later, what's going to happen? Let me do a different color here. This plane might be right here, and this plane may be right here. And what we're trying to figure out is what's going on with the distance. Here's the distance between them, then here's the distance between them, then here's the distance between them again. And they want to figure out how much is that distance changing. Okay, what's going on with that distance in between them. Okay, so we have to try to make an equation to figure out, well, how far How much is this changing? How much is going on here? So we have this case here, the distances from the airport. So they call it the westbound plane and the northbound plane. So if I make a generic equation, because it's always going to be at a right angle right here, here's the distance the westbound plane is from the airport. Here's the distance the northbound plane is from the airport. And this is the distance between the two planes. And that's the key right there. That's also changing. Unlike the ladder problem, this distance is going to be changing as well as those other distances right there. Okay? So to point a couple things out, this distance is getting smaller, the W, the length of the distance away from the airport is getting smaller and smaller because they're getting close to the airport, whereas this plane is getting bigger, the distance is bigger in because it's traveling away from the airport. We don't know yet, is that thing getting smaller or bigger or what? We're not sure. And that's part of what this problem is all about. Okay, so the equation is the Pythagorean theorem, this w squared plus n squared equals d squared. Now, they tell you the westbound plane is traveling 120 knots, all right? It's toward the airport. So remember, I just talked about w is getting smaller. That's why dw, and I'm not sure why they called it y, but we'll roll with that one right here. I believe they mean to call that dw dt. I'll change that right there because everything is going to be with respect to time, just so you guys know. So the point is, that is a negative 120, because remember, here's w, here's n, here's d. Because this is traveling that direction, w is getting smaller. N is traveling that direction, so n is getting bigger. This is the specific amount that w is changing. dw dt is negative 120, whereas dn dt, that other plane that's going upward, that thing is getting further away from the airport. That's why it's a positive 160. Okay, so they don't just tell you negative and positive. You have to understand the context, the problem, what's going on here. So this is what we have. Here's our two values. Now they tell us a half hour after the northbound plane passes over the airport, it is located at a distance of 80 nautical miles away from the airport. Now go back. Notice they didn't tell us that. Okay, they didn't tell you the 80. Notice in my original problem, there's no 80. What they told us was, where is it? How fast is the distance changing 1/2 hour later? So the one thing they told us is that our time is going to be half hour later. Now, where did they get this 80 from? Well, think about it. That plane going north is 160 knots. Now, if you're not familiar with that terminology, what it means is it's 160 nautical miles. That's what 160 knots is. 160 nautical miles per hour. It's like miles per hour. Just think of it that way. It's miles per hour in a car. So if you're going 160 miles per hour, in a half hour, you're only going 80 miles. So that's why you get this 80 miles right here, is because we were going 160, but we only went for a half hour, so it's half of that. Just like this one right here, this distance of W, it was 120 miles away, but because we went half hour, now it's gone 60 miles, so that's going to be 60, and that's going to be the second example they give us right here. Okay, so they've identified some things. Now, I'm not always a person where it's not always easy for me to identify this stuff right out of the gate. So I'll kind of show you my approach, which is the same. It's just a little different order. I want to go back to that equation, which is this one right here. Okay, this is what matters. The w squared plus n squared equals d squared. And like we did earlier, we have to go find the derivative of that. The derivative with respect to t. So this equation right here, I take the derivative with respect to t. Now the good news is it's an easy derivative. It's 2w, 2n, and 2d, but in each case, like always, because we're taking the derivative with respect to a different letter, w, I get a dw dt multiplied to it with the chain rule. The n part, I have the dn dt, and the last one has a dd, capital D, over dt. Each of those, that's the chain rule. So if you look at this, we have 6 different variables. We have W, we have N, we have D, and then we have dW dt, dN dt, dd dt. 6 different things, and this is again the important part to knowing what does everything mean. So, one more time I'm going to draw that picture to show you what we have. So, here's the easy part of the variables. N is this distance, W is that distance, D is that distance. Okay, those are the 3 distances, actual regular distances. Then the dW dt is how fast that thing is changing. Anytime it's a d something dt, it's a change. This is how dN dt is how fast this is changing, and dd dt is how fast that's changing. So if you remember what they've given us, they've given you some of these changes, they've given you some of these distances. And we have to look at these 6 and figure out, well, what in the world do we need to find? So I'm going to go back and forth. Remember the question being asked is, okay, where'd it go? How fast is the distance between planes changing? So they didn't ask you how far apart they were. They asked, how fast is everything changing? How fast is the distance changing? Sorry. So when they ask you how fast is the distance between planes changing, this is the thing they want you to find right here. Okay? They didn't ask you how fast is the first bound plane changing distance or the second plane. They wanted, and they didn't ask how far was in between the planes. They want to know at that moment in time how fast is the distance between planes is changing. That's the dd dt. So in order to find that answer, we need to find the other 5 variables. And they gave us all those. Okay, so remember, they told you the northbound plane, the distance is changing at a rate of 160. That goes in this dN dt. They told you the westbound plane is going at a rate of 120, but because that means the distance W is decreasing, that's a negative 120. They told us 80. Now remember, they didn't tell us 80, but they told us that it was a half hour later. So at the moment we freeze the picture, what we know is this is 80, this is 60. And we plug in these both into the Pythagorean theorem, and we can figure out, we can deduce that's going to be 100. So now you look at it. We know D, we know W, we know N, we know dW dt, we know dN dt. We know everything in this equation except for, of course, the one thing we're trying to find, d dt, but now we should be able to plug it all in and be able to get the answer. Okay, so we look at this, we plug all those in, plug each one. So look at this equation, this derivative we have right here. We plug in all those numbers, and now we divide, and right here on the right, notice this is a 200. So we take all of this and we divide it by 200, this 2 times 100. We get 11,200 over 200. We get our 56. That's telling us that's the how fast that distance between the planes is changing. Okay, that's the end result. So the good news is, the bad news is, let's start with that. It's a little awkward because there's so much going on. But the good part is all these problems are pretty much the same. And as you do a couple of these, you'll start to see that it doesn't matter what the problem is, you can do the same thing. Okay, so in this problem, suppose a point is moving in a circular path centered at the origin and radius 5. So there's a circle right here, radius 5. This point is moving around the circle. Okay, the graph has an equation of x squared plus y squared equals 25. Now they say when the point is located at negative 3, 4. So remember, it's just this point is rolling around the circle, and at this point right here, we freeze. And they tell us that the x-coordinate is increasing at a rate of 0.4 units per second. Now, when I say x and y, here's what I want you to look at. If you just look at where you are in terms of your y value, okay, when the point is, say, right, I can draw this here, as I'm rolling through, think about it, my y value is increasing, and it starts to increase pretty fast, but as you get to the top, notice you're not really climbing anymore. Okay, you're moving up, but the y value is like 3.1, 3.2, 4. Then my y value starts going down. Then it goes down more and the y value then starts to go up. That's just the y value. Now, if I look at the x value, notice if I'm just starting over here, my x is slowly increasing, then it's increasing a lot. Now it's slowing down. Then my x is going down and then back positive. So just talking about x's and y's, the coordinates, what's happening, that's increasing and decreasing, but they're increasing and decreasing at different rates. Like I said, think of elevation. Here, right here, it's moving up pretty quick while only going over a little bit, but it's moving up fast. Then for this next part, it's kind of just increasing height by a little bit. So even though this point may be moving constantly around the circle, your x's and y's are moving up and down at different rates. So what we have to do is we have to find an equation that has x and y. Well, they have it right here. This x squared plus y squared equals 25. Same as always, take the derivative of that. So going right to this important part. Let's take the derivative, then I'll fill in the blanks. So notice something about the derivative. A lot of these are kind of similar. It's derivative with respect to t. So that's going to be 2x dx dt. Again, a little typo. That's a t. Everything's going to have a dt on the bottom. Just listen on that part. Always going to have a dt on the bottom. So we have dx dt plus 2y dy dt. So that's the derivative with respect to t. All right? So now, what do you get? You got to plug in, you got to figure out what you're looking for. And the question they asked for was, how fast is the y coordinate changing? Well, y coordinate is right there. That's the question. Okay, they didn't ask what's the y value. If they said what's the y value, you give me that. But they asked how fast is the y value changing, meaning I want dy dt. So if I asked you what's the area, you give me a. If I tell you how fast is the area changing, you give me dA dt. So see the difference of the two. So if I want to find dy dt, I have to know x, I have to know dx dt, and I have to know y. Well, thankfully, they told us all these. They told us dx dt is 0.4. They tell you x because it's at a coordinate right here. X is -3 and y is 4. Those are the things that we're going to plug in to this equation right here. So that's what we're plugging in. Now again, there's a typo. That's supposed to be a dx dt. Both of these. Like that. Okay? So now we just plug in everything that we have. Now what they did, the shortcut they did was they divided both sides by 2, and that just simplified the problem. You didn't have to do that. Whether you did that or not, you're going to get the same answer. So now they plug everything in, and in the equation, which is right here on the right, we have a -3 for x, we have a 0.4 for dx dt, we have a 4 for the y, and now you solve for dy dt. And just to make sure it's clear, this becomes a -1.2 plus 4 dy dt equals 0. Then you get a 4 dy dt equals 1.12, and then divide both sides by 4, and that's how they get this 0.3. So they're saying that y is increasing at a rate of 0.3 units per second. So your y value is definitely going up. You can see it's going up. If they ask for it over here, you can see your y value is going down. So it just kind of depends on where you are in the problem, because at different points in time around this circle, sometimes x is increasing, sometimes y is increasing, sometimes they're decreasing, sometimes it's one and the other. It just depends on where you are in the circle and, of course, what direction's going on here. So that's, again, the example of related rates, something a little different. Now we'll get to one that fits in our theme of our course, our business, a little more. They give you a cost equation, 5,000 plus 2x. Revenue equation, 10x minus 0.001x squared. And of course, your profit is always the same, revenue minus cost. So the production output in 1 week is X flash drives. How many you're making in a single week? So they tell us production increases at a rate of 500 flash drives per week. So notice they're not telling you it's 500 flash drives. They're telling you that's the rate. So right there, you've got to think, what does it mean? Okay, flash drives is X. Well, they tell you right here, that means X is 2,000. This right here is a rate, which you think means dx dt. That's the 500. So you see the difference of the two. One is a rate and one is an exact amount. So that's where you get the two values. So in my equation here, we have 5,000 plus 2x for the cost. This one they gave us. So we want, I'm sorry, the question was find the rate of increase in the cost. So rate of increase in cost. They didn't say find the cost. They said find the rate of increase in the cost. That tells you I need a d something, dc dt. Well, all of these scream, go find the derivative. So I'm going to take this equation and take the derivative with respect to t. So look at that for a second. Now, one thing kind of weird. All right, look at it for a second. See if you can figure everything out. Then I'll point out. C, the derivative of that is 1, but because it's not the letter t and we're taking our derivative with respect to t, time, we'd use the chain rule. It's like a 1 dc dt. Over here, it's 5,000. Okay, now, you didn't need to write this. Just the derivative of 5,000 is just a 0. Get rid of that. And then the last one is the derivative of 2x. So I'll go to that. This is what matters right here. So you don't even need this first equation, but dc dt plus 0, this is 2 dx dt. The derivative of 2x is 2. The derivative, because it's not a t, the chain rule says put on the dx dt. So the equation that matters is, I'm going to write it right here because it's a little messy. dc over dt equals 2 dx dt. That is the equation that you need here for this problem. Okay? So now we have to figure out everything is. Now I left these things at the bottom of the screen from what we figured out earlier. Remember they told you dx dt is 500. So I can put a 500 right here. And notice we found that x is 2,000, but there's no plain x. There's nowhere to plug x into, and that happens sometimes. You basically don't need it. If you want to find the rate that the cost is increasing, you just plug in this and you get the cost is increasing at a rate of 1,000 units per week. Okay, and that's what we get right here. So sometimes it didn't matter. It doesn't come into play, and that depends on the equation, what it is, what you had. Sometimes you don't need to plug in every letter, every value given. So this is basically saying that you're increasing at a constant rate. If you have this 500 on the far right, it doesn't matter at what point x is. In other equations, it matters. When x is 1,000, it is one rate. When x is 2,000, it's a different rate. So it just depends on what the original equation was. So you find the derivative and you get the answer, and that's it. Okay, so in this next one, they're telling us same problem, I believe, but this time they want you to find the rate of increase in the revenue. So you'll see how this works. It's the same thing now, and I guess I shouldn't have erased this. X is still 2,000, and the rate of change, dx dt, is 500. Okay, but this time we're using the revenue equation. So again, we find the derivative with respect to t. So that's dr dt, and then we find the derivative of each of these. So like I said, I don't care for this middle step. I just go right to the derivative right here. dr dt equals 10, that's this derivative, dx dt, because x is not the right letter, dx dt, minus, excuse me, 2 times this, so it's negative 0.02, and then drop the power by 1. You get an x, then you get a dx dt. So dr dt equals all of this right here on the right. Okay, now they factored, just so you know, they factored out the dx dt. That's why it looks like this. You didn't have to factor it. You could have left it like this as well. It would have worked fine. So now what we do is we plug in the 2,000 for x. We plug in the 500 for dx dt. So this becomes 500. This becomes 500, this becomes 1,000, or you could use this equation over here, which is what they did in this example. So, excuse me, we get a 10 minus 0.002 times 2,000, and all of that is times 500, and that gets you a 3,000 per week. That's what the revenue is going to increase. Now notice this time, it did matter what the x was. We had to use that. Like I said, it depends on the equation. Sometimes the x drops off, so you don't need to worry about it. It's irrelevant. In this case, yeah, it really did matter where it was. It mattered what x was when you did this problem. All right, so now the last one is find the rate of increase in profit. Well, we have this equation, and now we have dp dt, took a derivative. These are all with respect to t, and it's a really easy problem. This is profit equals revenue minus cost, so dp dt equals dr dt minus dc dt, because there's no other letters here. We took all those derivatives with respect to t, and remember, we found each of these things. We found drt earlier at 3,000. We found dc dt at 1,000, which means our profit is increasing. Remember, this is not the profit. This is dp dt, which is the increase of the profit. How fast is the profit increasing? It's increasing at $2,000 per week. Okay? So that's our profit. All right, so now I'll show you a couple of these homework problems so you can kind of see how this works. Like I said, the good news is if you've already looked at this Chapter 9 homework, and you will in a bit, if not, you'll see that it's actually pretty good because there's not a lot. But as you could tell by these examples I've done, it does take a little bit of work. You have to think about these a little bit. You have to kind of talk your way through them. So let's look at the homework here. Oh, I might have to log back in, maybe. Okay. So here's the homework. It's got 29 questions, and section 6 only goes up to, I want to say, number 7. So there's only 7 questions out of this chapter. So I'm going to do a couple of them just to show you how they work. And then you should be able to do the first 7. All right, on this one, we have assume x and y are functions of t. So we're going to take basically our derivative with respect to t. For this equation, 2xy minus 2x plus 5y cubed equals minus 25, with the condition that dx dt is negative 20, x equals 5, y equals negative 1. So here's the equation. So when they say it's functions of t, it means go find the derivative of this with respect to t. Okay? Now the first part is the one that's going to be the most awkward, because remember, this is the product rule. We take 2x times y, and we have to do that product rule. So remember how that works. That's 2x times the derivative of y. Well, the derivative of y is just 1, but because we're with respect to t, that's a dy dt. Okay, now look over that carefully. Notice there's no dx dt because I'm not taking the derivative of an x. I held the x, the first part, 2x, to stay by itself, so there's no derivative of that. It's derivative of the y. On the product rule, now I take the y, not taking the derivative of it, just holding it, and I multiply that by the derivative of 2x, which is 2. Now I'm taking derivative of an x. There's the dx dt. Okay, so that's all for the first part. Now we do this derivative, which is negative 2, again, dx dt, because I took the derivative of an x. Then I take the derivative of that, which is 15y squared. Again, I took a derivative of a y, so it's a dy dt. All these are chain rules multiplying to the ends. And I have this. Now at this point, I could try to clean it up, but I don't need to. I don't need to factor. I have my equation with all my pieces. I'm going to plug all this into here. And remember, they want you to find dy dt. So that means I'm looking for dy dt, replace every other letter. Well, I know x, they told me it's 5. I know y, it's negative 1. So I'm just literally plugging in everything right above. Minus 2 times dx dt, oh, I'm sorry, They also gave us dx dt of minus 20. Let's go back a second. They gave us this one. So that's a minus 20. And this is a minus 20. Same thing, dx dt in both. And then up to here, they gave us y, which is negative 1. And the thing we're trying to find is dy dt. Okay? All right, so now, just cleaning things up a little bit. We have a 10 dy dt. We have a positive 40. We have another positive 40. And we have a positive 15 dy dt equals 0. Okay, so look at these. Remember, these are similar terms. They're both dy dt, so I have two of them together. I add the letters in front. I add the coefficients. I get 25 dy dt equals a minus 80. 40 plus 40 on the left, move it to the right, we get a minus 80. And dy dt equals negative 80 over 25. I can reduce that down, divide it by 5. What do we get? Negative 16 over 5. That should be my answer. And notice, type in exact answer. You can plug this into your calculator and you're going to get like negative 3.2. But when they say type in exact answer, they don't want a decimal. Now, especially a decimal that goes on forever. If I type in negative 3.2, it might work. Yeah, they counted it. But if it was a decimal that goes on forever and you had to round it, they would mark it wrong because there's no rounding. They want the exact answer. Anytime they say exact answer in simplified form, let me tell you, they actually want this fraction that I put right here. Okay, once in a while, like now it worked. I just wanted to try it and it worked. But if you would have plugged in negative, the fraction as it is, that's the answer. Okay, so that's it for that one. Make sure you understand that. Let's go to the next question. Okay. Okay, let me clear this out a little bit. Let's look at what number 7 is. Okay, so another one is like we had earlier here. We have C equals all of that. 80,000 plus 20x, R equals 200x minus x squared over 20, P equals R minus C, where the output in 1 week is X calculators, production showing a rate of 400 calculators per week, and output of 6,000 calculators. Find the rate of increase or decrease in costs, revenue, and profit. Okay, so let's identify our pieces here. Number 1, we have an X, our only main variable here. Which of these is X? So we have a 400, we have a 6,000. Remember, if you see rate, that does not mean X. This is X right here. This is dx dt. How many calculators I'm making, the rate of them per week is 400 per week, not at how many do we have made. Okay, so make sure you can identify that. If they tell you some sort of a rate, it's never going to be just a letter. It's got to be a d, that letter, over dt. D something over dt. So our first question is cost. All right. At what rate of production? I want to make sure I'm reading this right. Oh, okay. So this drop down, I think, is going to say increase and decrease. Yep, increasing or decreasing. So what we have to find is we need to find dc dt. That's the question here. So look at the equation. C equals 80,000 plus 20x. All right, so we want to find the rate of increase or decrease of C. So I take the derivative with respect to time. That's going to be dc dt. That's going to be a 0. This is going to be a 20, but because it's an x, I have a dx dt right there. So now we fill in the blanks. dc dt is 20 times dx dt, which is 400, which looks like it's going to be 8,000. Now, if it's a positive answer, that means you have a increasing rate for C. If it's a negative, you're having a decreasing. So this is increasing at a rate of $8,000 per week. And check that one. Oh, what did I get wrong here? Okay, costs. Oh, I didn't type enough zeros. That was my problem. There we go. I thought I typed 8,000. Sorry, 800, but 8,000 was our answer. There we go. Now we're going to do the same exact thing for revenue. So I'm going to clear out most of my screen here, and just to show you that it's a different formula, but it's the same process. Okay, so I'm going to go right here. The stuff I have in green, that doesn't change. That's part of the given of the problem. The rest of it will. So in this case, the revenue equation is 200x minus x squared over 20. So I'm doing the same thing where I'm going to take that with respect to t. So this is dr dt. This is 200 dx dt. Anytime you take a derivative of an x, it's a dx dt. This is going to be multiply the 2, so that becomes an x over 10. Make sure you see why it's x over 10. If I multiply by 2, it becomes, and drop the power by 1, it's a 2x. 2x over 20 is x over 10. And still, it's a dx dt right here. So dr dt equals 200 times the 400. Remember, dx dt is 400. Minus x over 10, well, x is 6,000 over 10, again times the 400. So now we multiply these all out, we get 80,000 this time, minus 600 times 400. So dr dt equals 80,000 minus 240,000, I believe. And that means we get a negative 160,000. Okay, I hope I did that math right in my head. That means my revenue is going to be decreasing. I'll get all that right. Yeah, it looks right. Something didn't feel good on that one. Okay, too many zeros this time. Now we're good. Okay, so my revenue is decreasing at a rate of $160 per week. And then our last part is profit. And remember, this is the easy one that we did earlier. P equals R minus C. We take this derivative with respect to t. And dp dt equals the dr dt, which we found earlier, at negative 160,000. We found it just now, I should say, not earlier, right now, that one. Minus the cost, which we said was 8,000. That looks like it's going to be negative 168,000. So our profits are decreasing at a rate of 168,000 per week. And that's it. Okay, so like I said, there's not going to be a lot of homework problems. These take a little more setup, as you can see. They're going to be a little bit more work. But you should, at least with this video, you should be able to do the first 7 problems of your homework. And then next video I'll record, we'll talk about section 3.7. A little more problems, a little easier topic, I believe. So give this your due attention, due time. Even though there's less problems, spend the appropriate normal amount of time on it, and you should be good. So if you have any questions, shoot me an email, and we'll look for the next video coming up shortly.